Welcome to a new test and teardown video. Today we're going to play with two a little bit different HP function generators. The main base unit is the 3300A function generator. It's a 2-channel generator. You can make those signs, triangle, square and all that, and then you can connect the output to the plug-in module, whatever that may be. The frequency range is, as you can see here, 10 times 10k, so that is 100 kilohertz, but the lowest frequency is 0.01 hertz. Really? So that is some span. I don't know what you're going to use those really low frequencies for. Maybe some sweep of some science experiments where you need some square or triangle to sweep. Well, definitely be a triangle sweep, right? And you need to perform some experiments. And yeah, I got two different plug-in modules. The first one here is the 3302A. So this is a trigger phase lock unit. And so you can input something and then you can phase lock your generator to this. There are like quite a lot of dials for the phase locking stuff. What is that? Frequency under or over 50? Yeah, so this is definitely something we're going to play with as well. And then in the end of the video, I'm going to play with the last plugin module, a sweep offset plugin. And here we can set up some, obviously some sweep offsets. I think this is going to be funny to see how this works and what this will do again. So let's start with this one. Let's look at the back before we power up. As far as I can see, this is an analog interface for frequency dial or frequency control. You can even input here. You got sync output, and then there is a short. So that means we're using internal frequency control. It also says here you need to remove the shorting bar if you want to input something here. 0 to 15 volts input. And it is correctly set for the correct voltage. Fuses are okay, so we are ready to power up. But hey, let's look a little bit on the serial numbers. This one says made in USA, and then it's 533. As far as I know, the first digit is numbers of years after 1960, right? So this means that this unit is from 1965. So let's look at the other one. See, there's no made in USA here. It says West Germany. And also this G is for Germany. And then the serial number is 640 it starts with. So that is number 6, is 6 years after 1960. So this is 66. So they're actually quite old, but in pretty good shape. I think we're ready to power this up. I've connected all 4 channels, one sync output and the A and the B output, and I'm ready to play with the phase trigger as well. So that is why I need 4 channels to play with this. Let's try and power it up. 1327 watts. And what do you know? we got output. I see some sync signals. So that is how it is, some insanely short pulses. All right, so I am in, oh yeah, this is my fault. I wanted to be in 1 kilohertz, duh. So here we go. Now we got 1 kilohertz. One is in sine, yes, sine and triangle. And that will be, yeah. Ooh, this pot needs a little bit of service. How is the other? Ooh, yo, yo. Can you see what happens when you operate a really old pot? But anyway, we got the 1 kilohertz output. It is a little bit low. Is it just me? No. And I believe I am in free running mode. So this is what we see here, right? It's really funny with the sync outputs. This is really good to trigger something external. When it's high and when it's low like this, then you can trigger positive and negative. They really thought of everything. This is super good. Oh, you got to see this. It is absolutely cool. I'm starting to play a little bit with this unit. And now both A and B, they're in triangle, as you can see here. And if both of them, they're in sine. Yeah, easy, easy. No surprises, right? Square, square. Okay, here we go. I think it's actually easier to see in the triangle. I am, of course, triggering on the external trick. So that means I can do whatever I want, right? So if channel A is in plug-in, then it's definitely from the plug-in module here, whatever is happening. But what if channel B's input is moving all the way up to A? Ooh, now it's a copy of the other one, but inverted. So that means I can do everything inverted. Isn't that just cool? So this is a way to do it. Just one little flip here. I kind of like that. That was really funny. So I think we should start to play with the plugin module. So both of them can probably go to the plugin, and then we'll see what happens. So now I'm playing with the trigger phase lock module. I am now in single instead of being in free run as we started. So now I'm single. So that means every time the trigger happens, it will perform a single sweep, right? So let's look at the output. We see a single sweep at the top here. Now I'm changing the frequency of that single sweep back to 1 kilohertz. My input trick is 500 hertz. It's a sine wave, but it can of course be any other waveforms. If you like it to be a pulse like that, we can also do that. And of course, you can see here how the time takes. So what I can do is I can change the frequency all the way. See, ooh, that was too close, right? So when I go too close, that means there's no more time to retrig. And what if yeah, you see what happens? Now there is no time, and then it will trigger at the next available pulse, and that of course looks a little bit jumpy like that. That means you're just using the system wrong. So yeah, single. We can also do multiple. Let's try that. I've been playing quite a long time with this multiple trick, and how the heck is that supposed to work? I mean, I'm also doing this entirely from not reading the manual at all, and this is kind of my thing. Let's see if we can figure out how to operate instruments without reading the manual, and then go from here. But the free, I mean the multiple, obviously what you see here is, yeah, we do get multiple. Yeah, fantastic, that is, right? So it seems like I get, how many is that, like 8 or 10? And then I am triggering at 100 hertz, and what you see here is the 1 kilohertz. So obviously we get all those multiples, and then there's silence, then it waits for the new trick. But see what happens if I change my frequency around 1 kilohertz. So I go now a little bit slower. Then, ooh, now it goes to 3. And then I go even slower, then it goes back again. And then back again. So there's, and then, what is that? And then back again. Now it's 700 hertz for my sine wave. Let's just crank it all the way down. Maybe, yeah, see here again. So I think it has something to do with multiples of when this happens, right? So if there is another curve, it needs to do that curve until it's, yeah, it needs to do that sine wave until it's completely done, right? And then you see, but there's some kind of a problem here. It is not doing it here, so there is a little bit of problem with this multiple. It is not easy to understand, at least not here, right? And then we go back. Well, it's good and stable. So there's a little bit of funniness with that. Well, the funny unstable multiple. And I've of course tried to poke around with all these things, and nothing really changes this funky behavior. I am so sorry, guys, but I am not able to show you the phase lock. See here in 3 run, I got an input that's like very close to the output frequencies. It's almost not jumping, right? And this is in free running. And even in free running, it seems like it is trying to lock itself. Can you see? So something in here is kind of locking it a little bit. There's some sort of an influence on my incoming signal. So now I go to phase lock, and then the output just goes absolutely crappity crap. And there is no sync output, that's the blue one. It's just not there. And I've been trying to poke around with internal and manual and all the things here, but there's nothing seems to be working. And I don't have any indication here as well about cal or on cal or the phase or the anything. The only way that I can make this indicate something is to change the frequency a factor of 10. Well, sometimes I could. I don't know what I did. But there's just no way for the phase lock to work. Too bad. I think it's time to open this thing and let's have a look inside, because I kind of give up. This is boring stuff when it doesn't work. So that was the lid off. It looks a little bit like the main unit is actually also some sort of another case inside the case. So maybe there's a way to unplug this as well. At least it's mounted in some plastic all the way around. We got some transistors and stuff here, so maybe that's just the way it's built. So this is definitely the plug-in module. Let's just try and pull it out. The way that it works with this plug-in module, that is this screw. So it just goes like this when you want to lock it, see? And then like this when you want to unlock it. It's that easy. Ooh, that looks a little bit dodgy. Yeah, maybe we need a little bit of cleanup here. Maybe somebody's been soldering around here and doing some... Is this one actually connected? This is my trigger stuff. I think I'll have a little look here and see if I can find What have we got in here? Okay, we need to open it a little bit more. Hang on a second. So let's look a little bit inside. I don't know if you can see this, but I saw it immediately. That capacitor here. What do you think about that soldering? And this goes on and on. That one as well. Half of those components, they're not connected. And it really looks like somebody with bad soldering skills did service on this unit. I mean, look at all those components, that's like really bad. What is this kind of soldering? Oh no. You don't need to send your stuff in for service to somebody who don't know what they're doing. Hey. Because now it's going to take a lot longer to fix this. What kind of poking around with all the different parts here? Is this like, look at all the damage around the parts. Oh, I don't know, that is going to take a little while here to clean up all this mess and see if it actually works. But definitely this one was defect and somebody tried to repair it, and that is of course why it was scrapped in the first place. And one of my buddies saved this one for inspection and check out here at my lab. But I'm just not able to offer a 1,000-hour repair job on this one. Oh no, look at the dodgy. Oh, that is sad to see. But that's definitely why this trigger module here, or face locked module, is not working the way it was supposed to do. It's clearly not a user fault. I can't be that dumb. All right. Yeah, shit, man. But look at how it looks on the outside. It's just beautiful, beautiful condition. Let's look inside the generator module, or the generator part of this unit. Again, what do you say? This is a true HP classic design. See all the individual shielded metal rooms. It is just how you do good stuff. So sensitive and critical stuff. That'll be the A and the B, I guess. Yeah, DC balance is that pot for the two outputs. I mean, how about we try and pull up some of those boards? What is that sexy module here? Mounted with a lot of screws. And of course the power supply is in its own room. That is no surprise. Let's look a little bit on the different PCBs got here. Let's start with the power supply. That is really, really nice and beautiful. No one performed any kind of service or damage to the power supply. Can't even see on the contacts it has been up and down or anything. So I really like the test point indications like this. So that means you can easily figure out what is wrong by just measuring this. On the top, easy accessible. Oops, somebody did actually service. So we got some of those ugly solderings. No, what is that? So this transistor was replaced. or just resoldered, because it looks exactly like the other one, and that one was not replaced. Let's look at the other side. Yeah, so that will be the power supply. So look at all those diodes and all the different resistors here. This tells me we're talking about some changes in sweep times and stuff. So I bet those diodes that will be connected to this one, right? So then you could change the different resistors. So this is a part of the sweep and stuff like that, right? And then the next one here, that's also something like that. As again, here we go, some other resistors, high precision stuff connected, and then we see some, this capacitor is marked so with number 41, but I saw another one down here also 41, so that means that guy number 41 measured those two capacitors. And again, this will be the A and the B outputs. So I put them here so I don't swap them by accident. And again, a lot of service was indeed performed on this unit, but I see 1965 on that transistor, and that will be the date when this unit is from 1966. So that is a little bit weird. Why are we seeing those kind of really ugly solderings? Like somebody changed half of the transistors, actually all of them, on this board, and they did a terrible job. Look how bad this looks. This is not how you do it. And let's look at the other output amplifier. It's clear that the transistor solderings, they're not the same high quality as everything else on this board. But anyway, this module kind of works, so I'm not doing anything to change this, but I'm just a little bit sad to see people solder around like this and don't clean it up and don't perform proper solder jobs. Look at this. Like, is this really soldered? So this is the same board, same transistors, just resoldered it and cleaned it a little bit. So let's look at the bottom. Of course, when we take away the first lid, then there's another shield inside. That is typical HP. They want to do it right. Now with the lid removed, look at all those trimmers and power transistors. They are mounted in a really nice and cute way. So that will be the push-pull transistors for the output drivers. I mean, this is beautiful. And that will be the super cute module. Is that a... yeah, that is a coax cable, definitely. Also what I saw is the mains entry is actually cracked, so we need to be careful. And there's, as you can see here, there's actually a mark on the top of the mains capacitor. See, this one actually touches this inner plate here. This is not so good when you kind of grind through this, so we need to add a little piece of tape on the inside. Ooh la la, we're inside. That is a cool module. Look at that. Isolation material and all stuff. And what have we got in here? I bet this is the oscillator and all the part related to oscillation. So the frequency stability and all that. I think we should maybe take this module up if we can. And of course that was possible to take this up. But look, something tells me that this unit runs very, very hot. So you know what this is? This is indeed the oscillator. And that is the filament bulb that is used for amplitude compensation. And look at all the transistors here. They are like corroded and whatnot. Really, really rusty stuff. And it tells me, you know, look at the power resistors. They're distributed all the way around. So they're going to heat up this PCB in a nice and equal way. And here in the middle, this is the temperature sensor. This is probably an NCC, and it's connected to some of the components here that will do temperature regulation. So what we see here is actually an oven controlled temperature stabilized oscillator for low frequency. But my god, they're rusty, crusty all over the place. There's just a tiny little isolation between those two transistors. And if we look at the other side of the PCB, yes, of course, there was actually performed some sort of service. So some of the transistors, they were like replaced this one. But anyway, so far it actually works. So the oscillator is nice and stable. So now I'm going to power this up again and play a little bit with it and see if I can measure current consumption drops after a few minutes when this gets hot and stable. That is interesting. I did actually not expect to find this kind of level of ingenuity. Oh. I spent the last half an hour playing around with the power consumption, and while I was doing that I also played with the maximum and minimum and symmetry of the frequency adjustments. So after fine-tuning all that, I'm actually able to get the frequency settings way below 10%. So that's quite good. So I think this is about 7. Look at that. And it just goes on and on. I'm really happy about that. So now it is very, very accurate. And by the way, I am not able to measure any power consumption change over half an hour. It's just 27.3 watts, and it's just constant. From the first second I turned this on. So I mean, maybe this NCC and temperature regulation and stuff is not working, and maybe this is why it is so black and dark in here. Of course, I got another unit, so I'm going to test that now, and that's going to be a lot more fun to see if there's any compare in power consumption. By the way, if you happen to get a unit like this without the plug-in module, there's no output. So this free run mode actually shorts one of the pins here to make this run. So there's a run enable kind of thing. This signal is also used for triggering and re-triggering all sorts of things. So that is why you need a plug-in module, or at least you need to short this pin to get this unit up and running, right? Just so you know. So this is the other unit. Of course, I didn't get any output, and it was using like 40 something watts. So I removed the plug-in module and I put in the old module in 3-run mode. So now I got output, but still this unit is using 10 more watts. And also, if you take a look at the output, can you see it's jumping? This is unstable behaviors from probably the power supply, a ripple or something like that. So I need to power this off immediately and open and check for hot components. I mean, 10 watts too much, that is not normal, and this is definitely not okay. So let's look a little bit. This unit uses 10 watts too much. I don't know if I can show you this. So this is the power supply area. So the right side is that is the negative supply, and the left side is the positive supply. I mean, this one lights up quite a lot more. So that reveals that, yeah, something is using power. And then I'm kind of searching around here. So the two output drivers, they're exactly the same temperature. So this tells me it's all right. But what I'm going to do is I'm going to power up the other one and then kind of compare side by side the temperatures when it is running. So this is my plug-in module here. I don't see anything scary, like 50 Celsius. So yeah, we see some resistors actually do get a little bit hot. Of course, this is cheating using a thermal camera. It's just way too easy to pinpoint hot stuff and potential problems. I can even see the oscillator module, that one is actually warming up in this unit. Also here on its side. So maybe the other unit, this is not happening, and maybe this is the problem. I mean, the other one is the problem for not using all this power. So maybe this power is really the normal state. This is so weird. So the other one uses exactly 27 or 28 watts, no matter if I plug or unplug this module. Weird? I don't get it. I found the problem. So this is the old one that actually works, or, well, no. This one is the one that don't work. See? This is the oscillator module, that one. It's supposed to be containing all sorts of thermal stuff, right? Ice cold. Isn't that cool? So this is why this unit is not using all that power. Because everything else looks exactly like the other one. And the output drivers and all that stuff. So yeah, that is why we're missing 10 watts. Let's look a little bit in the manual. See what I said about the plug-in module. So if you want to run this unit without a plug-in module, all you have to do is make those 4 connections into the plug-in connector, and then you'll be able to get sine wave up and running. So this is a free run mode. Just remember to read those HP manuals, because sometimes you find some funny things. I let this module run for an hour, and now I can see that power consumption is going down all the time. So this reveals the regulation has begun. I mean, the temperature has been reached inside this oscillator module. So so that is perfectly fine. This tells me that this unit is working as it should be. And you can really see here on the thermal image. The temperature is 37 on the top, and I think I got, if I measure here on the background, 20 something. And if you don't have a thermal camera, you can easily feel the heat by touching this unit. And of course, just check the power consumption. It is going down, and it takes like a half an hour to 1 hour. And now the unit is supposed to be perfectly stable. So now I can focus on the ripple problem. Remember, the outputs, they're jumping like this, and that is clearly power supply ripple or something else inside the unit I need to fix. I've been playing a little bit around with the power supply ripple, and yeah, okay. We see here, actually, power consumption from the sine wave is visible on the power supply, and also the spikes from all the start and stop of the oscillator, that's also clearly ripple. And what you see here that is moving here, that is the mains ripple as well. So let me show you guys what happens if I change, see, the curve form, or the waveform, right? See, I change this, I can change the power supply. So that tells me the capacitors here, they are not super good. So that's just how it is, I guess. If you're rich, you could of course change this to more modern stuff, but maybe it's also a ground loop problem. I could of course put the scope down there and measure on the ground and see if that is stable, and there's a lot of stuff I can play with if I really want to, but it's a lot of fun. So let's play a little bit more with the sweep offset plugin. And what is it really doing for us? So there is this off, first of all. So if we hit it down to off, that means none of this is going to have any effect. And here is our nice and stable outputs, and that is all perfectly fine, right? So when I click it into on, can you see that the sweep is now modulating the frequency? And if I dial a little bit up on the width, can you see more and more and more? And the frequency of the repeat is about 1 hertz. Can you see that? 1, 2, 3. Okay. So here's the frequency of the modulation or the change. So it's set by the dial here. So there's another little sawtooth generator here. I still haven't figured out what they do, because they don't do anything at all. No matter what I do, there is no change whatsoever on my scope when I'm poking around with those. And the 3 dials down here, absolutely no change whatsoever either. So that is maybe because this is the external input. So since we're not using external input, but we are using the internal, that means they will not have any effect, right? But it's difficult to actually see what we're doing here on the scope. So I think I'll try and put a speaker on here, and let's hear if we can hear this. So now this is already annoying. scary. So now when we are done driving everybody nuts with all that noise, let's look inside this sweep offset plugin. And of course it can go to really low frequencies, like this 0.01 Hertz. So that is of course why you see this super big capacitor here. No, the other capacitors are, I think half of it is up there and the other half is down here, right? Quite a lot of trimmers for this quite simple sawtooth oscillator. And look again here, a lot of stuff. But this module really works the way that it was supposed to. All I had to do was to massage the on-off switch here a million times, and now it actually goes on and off when I wanted to, so that was quite easy. And the classic HP design with the connectors, so you can easily pull up the boards and do service. I mean, it's really well made the way you're used to. I'm just not able to get any schematics of either the 3304 or the 3302, so that is a little bit bad. But here you go. Now I will put this beautiful unit back together.